Mr. Cannabis.
Growing mediums are important for plant growth, health, and development, as they serve several key functions. They provide a reservoir for water holding, nutrient holding and exchange, a zone for gases exchange for the plant root system, and to anchor the plant's roots to give the whole plant stability. There are different physical characteristics of growing mediums that affect plant health, including bulk density, soil porosity, water holding capacity, air-filled porosity, container limit or drained upper limit, permanent wilting point, and cation exchange capacity. Container shape can affect air porosity, as weight of water and media can compact the lower media. Let's explain that last one first. Water is pulled down through the pot and drainage holes via gravity. Gravity in the container is a constant, but the gravitational potential at the container's top is higher than at the bottom. This is because the water within the media acts as a single body, so the weight at the top is pushing down on the media below. Water is attracted to particles by adhesion, cohesion, and surface tension, which results in capillary action, the movement of water within spaces of a porous material, which resists gravity. You can see this by taking a sponge and soaking it in water, then lifting it out flat and letting all the water drain out. Then you turn it on its side and more water drains out. Then turn it vertically and the last of the water that isn't bound by capillary action will drain out. Bulk density and soil porosity is actually what I was measuring here for the Ministry of Transportation of Ontario. Taking core samples, drying them in ovens, weighing them, grinding them in pestles, removing the rocks, and then warming the water to remove all the oxygen in the distilled water, to eventually measure the actual density and porosity of the soils left on the sides of highways after construction. Bulk density is a measure of the density or compaction of the media. It's the calculation of dry weight of the media divided by its volume expressed in grams per cubic centimeter. Soil porosity is the percentage of the media that are spaces or pores, considered either macropores or air-filled porosity, or micropores, water-filled porosity. And while the difference can be measured, macropores being 0.05 to 0.075 millimeters in diameter and above, and micropores being any size under that, but the main takeaway is, as their air-filled or water-filled names suggest, it's whether the spaces are small enough for water to be bound by capillary action to the media, or large enough that the water within the pore would weigh too much and drain out. Either pore size can be created simply from the manufacturing process, or the parent material, or from expanding gases within, or from root growth and death, or from insects and worms within the material. This is why people say worms and other soil insects and microbes are good for the garden. The pores affect moisture availability, aeration, heat transfer, and fertility within the growing mediums. Soil structures can either be granular, blocky, lenticular, platy, wedge, prismatic, or columnar. A mix containing coarse particles has fewer but large pores, which permit air to re-enter the media following irrigation. On average, most mixes contain 10 to 30% air following irrigation. A mix containing fine particulate has more but smaller pores and a greater percentage of water holding capacity. Components with smaller, finer particles and pores, such as sphagnum peat moss, processed coconut coir, and rockwool, hold more water, whereas those with larger, coarser particles, such as pine bark, perlite, and expanded clay pellets, hold little water. The percentage of each component making up the mix will determine the drainage of the container, or drained upper limit. Water holding capacity is a measure of water in soil at total saturation, with every soil pore space completely filled with water. Container limit, or drained upper limit, is the amount of water that a particular media holds after drainage has practically ceased. DUL replaced the old term field capacity. Container limit is used primarily for indoor or containers, and drained upper limit for outdoor or fields, hence why it replaces field capacity. but all three terms describe the same thing. Permanent wilting point is the amount of water in soil held through capillary action to the soil particulate at a Bay force stronger than 15 bar or 225 psi. It represents the minimum amount of water available to the plant, as plants cannot uptake past that limit. The soil water between container limit and the wilting point is called the plant available water, which is the amount of water that the plant can utilize. I'm always in favor of having a decently low PAW for several reasons, but I'll explain those more in section 6.5 watering practices. Just keep in mind that you don't want a media that holds on to too much of its water, though that does apply more to containers than planting in the ground. Particle density is the size of the average particulate in the media. Sizes generally fall between 2.6 and 2.75 grams per cubic centimeter for mineral particles. Organic matter weighs much less than the equal volume of mineral solids and often has a particle density of 1.2 to 1.4 grams per cubic centimeter. You can measure soil porosity with the following formula. This will indicate the percentage of the soil that contain pores. So if you have a bulk density of 0.1 grams per cubic centimeter and a particle density of 1.2 grams per cubic centimeter, our equation would look like this, which gives us the soil porosity of 91.7% of the total volume, which is a nice fluffy potting mix. Of course, this is a measurement of total porosity and doesn't give us a ratio of micro to macro pores within your particular media. Overmixing and fluffing, or using inadequate equipment for fluffing compressed bale growing media, can damage the structure of various components within the media, which will decrease the porosity and structure. Pre-wetting media to 48 to 52% moisture at the fluffing stage will help maintain its structure and performance. This is why compacted bales come pre-moisturized, so that the structure is more pliable and will resist breakage, keeping the desired macropore to micropore ratio of the mix. Cation exchange capacity, or CEC, measures the soil's ability to hold on and exchange cations. Cations are positively charged nutrient ions like calcium, magnesium, sodium, potassium, and ammonium that are held on to negatively charged sites on organic matter and clay surfaces. In order to come free from the site, they must be replaced or exchanged by another cation, generally hydrogen. The exchange occurs when the nutrient cations are attracted to the charged surface of cells within the root, called cortex cells. The plant root releases a hydrogen ion, called a proton release, which exchanges site placement on the organic matter or clay, balancing the charges. Proton release helps lower the pH in the soil of the immediate vicinity of the root, creating a more acidic environment that increases the solubility of certain nutrients, such as phosphorus or iron. High CEC soils obviously have a greater capacity for cation retention and exchange than lower CEC soils. Plants can grow in potting mixes that have a wide range of CECs, but substrates having a relatively high CEC levels, from 50 to 100 milliequivalents per liter, supports a consistent cation supply. Commonly reported cation soil reports include potassium, magnesium, calcium, hydrogen, and sodium. A CEC report on a soil test is estimated using reported potassium, magnesium, and calcium values. The reported values are then converted to milliequivalents per 100 grams of soil and added together to estimate the total CEC. The numbers will be the same if reported as centimoles per positive charge per kilogram, which is just another way of measuring it. Organic matter has more exchange sites than clay particles, and clay more than sand. Increasing a soil's CEC can be achieved through organic matter additions, crop rotation, or cover crops. Now, just to avoid any confusion, even though I do keep saying organic, CEC is generally just an issue for organic or field growers. They have to constantly consider how many cations are being held within their soil, which isn't something that a grower feeding typically synthetic fertilizer needs to worry about. Now, it can slightly affect the pH of the solution in the root zone, which I'll discuss a bit more in the next section.